The transition elements d block. Position in the periodic table. The d block occupies the large middle section of the periodic table flanked between s and p blocks in the periodic table. The d orbital of the penultimate energy level of atom receives electron giving rise to 4 rows of transition metal, that is 3d, 4d, 5d and 6d. All these series of the transition element are shown in a table electronic configuration of the d block element. In general, the electronic configuration of outer orbital of these elements is n-1 d1 to 10, ns1 to 2. The n-1 stands for the inner d orbital, which may have 1 to 10 electrons, and the outermost ns orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between n-1d and ns orbital. Furthermore, half and completely filled set of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configuration of chromium and the copper in the 3D series. For example, consider the case of chromium, which has 3d5 4s1 configuration instead of 3d4 4s2. The energy gap between the two sets 3d and 4s of orbital is small enough to prevent the electron entering the 3d orbital. Similarly, in case of copper, the configuration is 3d10 4s1 and not the 3d9 and 4s2. The ground state electronic configuration of the outer orbital of transition element are given in the table. The electronic configuration of outer orbital of zinc, cadmium, mercury and Cn are represented by the general formula n-1d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation state. Therefore, they are not regarded as a transition element. The d orbital of the transition element protrude to the periphery of an atom more than the other orbital, that is s and p, and hence they are more influenced by the surrounding as well as affected the atoms or the molecules surrounding them. In some respect, ions of a given Dn configuration n1 to 9 have similar magnetic and electronic properties. With partially filled d orbital, these elements exhibit certain characteristic properties such as display of a variety of oxidation state, formation of a colored ion, entering into the complex formation with a variety of ligand. The transition metal and their compound also exhibit the catalytic property and the paramagnetic behavior. All these characteristics have been discussed in detail in this unit. There are greater similarities in the properties of the transition element of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics and their trends in the horizontal row, particularly the 3D row, and then consider some group similarities. General properties of the transition element. We will discuss the properties of elements of first transition series only in the following section. Physical properties. Nearly all the transition elements display typical metallic property such as high tensile strength, ductility, malleability, high thermal and electrical conductivity and metallic luster. With the exception of zinc, cadmium, mercury and manganese, they have one or more typical metallic structures at normal temperature. The transition metal, with the exception of zinc, cadmium and mercury, are very hard and have low volatility. The melting and boiling point are high. Depicts the melting point of the transition metal belonging to 3D, 4D, 5D series. The high melting point of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to ns electrons in the interatomic metallic bonding. In any row, the melting point of these metals give rise to maximum at D5 except for anomalous values of manganese and technetium and falls regularly as the atomic number increases. They have high enthalpies of atomization which are shown in the figure. The maxima at about the middle of each series indicate the one unpaired electron per d orbital is particularly favorable for strong interatomic interactions. In general, greater the number of the valence electron, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, the metals with very high enthalpy of atomization, that is, very high boiling point, tend to nobble in their reactions. Another generalization that may be drawn from the figure is that the metal of the second and the third series have greater enthalpies of atomization than corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal metal bonding in compounds of heavy transition metal. Variation in atomic and ionic sizes of transition metal. In general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of the d electron is not that effective, and hence the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerging when atomic sizes of one series are compared with those of the corresponding elements in other series. The curves in the figure 8.3 shows an increase from the first 3D to the second 4D series of the element, but the radii of the third 5D series are virtually the same as that of corresponding members of the second series. This phenomena is associated with the intervention of 4f orbital, which must be filled before 5D series of the elements begin. The filling of 4f before 5D orbital results in a regular decrease in the atomic radii called as lengthenoid contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lengthenoid contraction is that the second and the third D series exhibit similar radii except zirconium 160 picometer and hafnium 159 picometer, and have very similar physical and chemical property, much more than that expected on the basis of usual family relationship. The factor responsible for the lengthened contraction is somewhat similar to that observed in an ordinary transition series and is attributed to the similar cause, that is, the imperfect shielding of an electron by another in the same set of orbital. However, the shielding of one 4f electron by another is less than that of 1d electron by another, and as the nuclear charge increases along the series, there is fairly regular decrease in the size of entire 4Fn orbital. The decrease in the metallic radius coupled with increase in the atomic mass result in general increase in the density of these elements. Thus, from titanium Z is 22 to copper Z is 29, the significant increase in the density may be noted in the table. Thank you.